Good morning, everybody. You ready for some chemistry? So I took a look at my notes this morning, which I hope look better in your notes, to be quite honest. I think I still have some improvements to add into here. Like, for instance, forgot to remind myself in my notes to talk to you about prefixed units more. We said there are base units and prefix units, and I actually wanted to go through those prefixes with you. So I know we kind of moved past this, but I do want to take a step back and look at the prefixes before we apply it today in some calculations. And then there was one of the units that we talked about that I didn't do a good job of addressing in its entirety. So I want to take a second to look at that too. So first, we had talked about some units like mass, temperature, length, time, and then some derived units. And we said that volume has what derived units? What combination of units? Cubic meters. Good. So meters times meters times meters, or cubic meters. And what I just completely left off of my notes was a very important conversion. In chemistry, when we talk about volume, we do sometimes use cubic meters. It can be useful. Cubic meters oftentimes better describe solid objects. If we're describing a liquid, cubic meters isn't always as useful. So what unit does cubic meters relate to that helps us describe the volume of a liquid? It's another unit for volume. And it has a relationship to cubic meters. Liters. So 1 cubic meter is equal to 1,000 liters. And I remember the first time I taught this course, I actually thought, well, liters is just a unit because it's a base unit of volume. But you can't get liters without having that relationship to cubic meters, and by being cubed, inherently cubic meters is not one thing, it's kind of derived. You have to have multiple. So that was the important connection I wanted to make, was the connection between cubic meters and liters. Okay. Actually, yeah, kind of along that similar note, when we talked about density, I think I told you guys that we report density with what units? Did I give you the units? Good. Not kilogram per meter? Did I give you kilogram per meter? Good. Kilogram per meter per cubic meter. Now, it's not a direct relationship, so I'm going to say this is approximately equal to. There's some proportionality here. There is actually a symbol that we can use for proportional. But this is similar to reporting things with units of grams per cubic meter. If you've got something that's incredibly dense or maybe incredibly large, you might want to talk about its density in kilograms per cubic meter. If you've got something that's smaller, grams per cubic meter. Another similar way to report density is to take these cubic length measurements and convert it into liters. So liquids, especially in the chemistry lab, are often reported with density of grams per milliliter. Puts it on a scale that's a lot more feasible to measure and talk about. All right? Now the prefixes. We're already looking at some of them. Prefixes take us from our base unit and either scale that unit to represent a larger quantity or to represent a smaller quantity. So there are different ways to do this. Some people like to have this represented in columns. I think today I want to try and have us represent it on this linear line. And we're going to look at our base right here in the middle. And we're going to say, what if I want a unit that describes something larger than the base? What if I want something a unit that describes something smaller than the base? So, first of all, something that is 10 times smaller than the base. In scientific notation, we can say that this is times 10 to the negative 1 of the base. 1/10 the size of the base. And this is given decimeter, or excuse me, deci. I'm thinking about applying this to meters. And we give that the symbol small d. If it's 100 times smaller, 10 to the negative 2 centi. And we give this lowercase c. 1,000 times smaller, 10 to the negative 3 milli. Which kind of feels weird, right? Because a million is not 1,000, but we still say that a millennium is 1,000 years. So milli, represented by lowercase m. I don't think I made my scale long enough because there are a few more I want to do on this side. There are divisions between here where I can do 10 to the negative 4th, 10 to the negative 5th, but the next most common is 10 to the negative 6th. Someone other than Ryan know this one? What prefix do we give to something that is 10 to the negative 6th, or in other words, 1 million times smaller than the base? Micro. And what prefix, or sorry, what symbol do we give this? Micro. U? Yeah, it looks like a U. It's actually the Greek letter mu, so that relationship between micro and mu. It looks like a silly U. Or if you're not careful and you're far away in the back, it kind of looks like an M. But it's meant to have that squiggly line coming off the bottom. There are so many that go in this direction. I think one more that is incredibly common, especially in today's day and age, 10 to the negative 9th. Nano. And this one's easy, 9 nano. And the symbol? N. Then there's femto. No. Then there's pico, 10 to the negative 12th, and femto, 10 to the negative 15th. Not incredibly common, but if you want to talk about the scale on which chemical reactions take place, they take place in femtoseconds to picoseconds. So I can't tell you in seconds how quick a chemical reaction takes place, but I can tell you on a much smaller scale how fast reactions take place. But it's not as common to see them until you get into much higher levels of chemistry, so I have a feeling few of you are ever going to deal with pico and femto, and you'll get readjusted to it by the time you need it. Let's talk about the other direction. Things that are larger than our base unit. 10 to the 1, 10 times larger. Ryan, you got this one? Oh. Anybody know 10 times larger? What would you guess? So like take your base and multiply it by 10. I don't think we'll call it a trillion times later. Oh, not 10 to the 10. 10 to the 10 is actually 10 billion. Gram is a unit. So if I'm saying I have something that's 10 times larger than a gram. Deca. And what symbol do we give this since deci already uses little d? Big D. What if it is 100 times larger, 10 to the second times larger than the base? What would you guys come up with?
Harvey wants to say like mega, but
Okay, so mega, what does mega make you think of? Why is your brain going to mega? Fair enough. You're close, actually. Hecta. Edgar, were you going to say that?
No.
Your relationship here might be between 100 and hecto being h, right? The relationship there is just h. Hecto. And this one, because we haven't used a small h, we can give this the symbol small h. 1,000 times. Kilo. This you should all be fairly familiar with if you've ever run a race, like a 3K or a 5K. You're running a certain number of kilometers, 3 kilometers, 5 kilometers. And then again, we can do 10 to the 4th, 10 to the 5th. They're not as common. 10 to the 6th. Brian?
I already forgot. Mega.
Mega. Good. And the symbol that we give this. Good. We can't do little m because milli already took little m. So this we give capital M. I don't know about you, but my capital M's and lowercase m's look very similar. So I actually draw them different. I take a ton of effort to draw my capital M just so that it's got nice rigid lines and I can tell it apart. Or if you've got scale, you can just make them larger or smaller. I don't think that we'll go past that. Ryan, did your notes from Realchem go past that? Okay. They're worth putting on there. Giga, at least. 10 to the negative 9. Sorry, 10 to the 9. Giga. I don't know, actually. I think Giga uses a capital G, despite not really using a lowercase g anywhere else. And 10 to the 12, which I don't think we'll see all that much. But you do hear about it in terms of storage nowadays. I remember the first time my dad bought a 1 terabyte hard drive. He was so impressed that this thing could store a terabyte of information. And nowadays, we use like a terabyte of AI data in a single day, all of humanity does. So there's this huge increase in terms of scale. All right, now I want to point out something. The scale that I've put on the bottom is in relationship to the base. But if you are going the other direction, if you're starting at a prefixed unit, then the relationship flips. So if you have a terabyte of information, then you actually have 10 to the 12 bytes of information. Yeah? If you started, so actually I think I want to say that a little bit different. If you're looking at this unit, it is this many times larger than the base, or this many times smaller than the base. But if you want to get to that number from the base, let's look at doing some conversions. This idea of unit conversions is referred to as dimensional analysis. I'll be honest, dimensional analysis never really made sense to me. The math made sense, but the term never made sense. So I just want to clarify. We are literally analyzing the dimensions of something. The dimensions of its weight, the dimensions of its length, the dimensions of its volume, the dimensions of whatever. And then we're changing those dimensions. So before we get nitty-gritty with chemistry units, I want to talk about units that you guys are all familiar with. So I went to the store this morning and I bought 48 donuts. And I didn't bring any for you. Just kidding, I didn't buy any donuts. A good unit to convert donuts into something smaller would be dozen. A dozen is a unit, correct? A dozen represents how many individual things? 12. So I'm going to change my dimensions from donuts. So I'm going to do this multiplication. Some people actually don't like seeing the multiplication sign, and instead they use this box method. One thing that trips people up with the box method is that nothing is going to go here. Well, not 0, nothing, but actually 1. I have 48 donuts per existence. 48 donuts per 1. 48 donuts per me. Does that make sense? Now, I don't want to talk about donuts anymore. So just like math, I need to be able to cancel that out. So I'm going to multiply by donuts on the bottom. Because as you can see, donuts divided by donuts doesn't give me donuts anymore. Number one rule in dimensional analysis, show your units so that you know whether you are multiplying or dividing appropriately. Now I want to get into dozen, so I'm going to put dozen on top. Maybe I wasn't sure whether dozen should go on top or bottom at the beginning, but now I do know, because donuts has to go on the bottom to cancel out. What is the relationship between dozen and donuts? 1 dozen, 12 donuts. These are the numbers I'm filling in. The numbers of the relationship correspond to the individual units. Alina, can I put 12 on top and 1 on bottom? Can I say 12 dozens is 1 donut? No way. Instead, 1 dozen is 12 donuts. So now I've got math. 48 times 1 divided by 12. And the math with my units. I'm only left over with 1 unit. What is 48 divided by 12? 4. Feel free to use your calculators, even when you're doing simple math, because I don't want you to second guess yourself in your head. And my unit here, dozen. What I have just done is changed the dimensions of my analysis. No, changed the dimensions of my measurement, of my information, and essentially changed the scale. I have a much smaller number. What has happened to my unit? Does my unit describe more things or less things? One more time. Does my unit describe more things or less things now? Ignore the number. A dozen represents 12 individual things. So this is a larger unit with a smaller number. So, rule of thumb, when the unit increases, donut to dozen, base to hecto, base to mega. When the unit increases, what happens to the number? The number decreases.
Is that true of all dimensional analysis?
All dimensional analysis, unless you're changing more than one unit. And if you make two changes to two different units, now you have to consider, are they compounding or going against each other, right? If I make one unit bigger and then the other one smaller, do I even see any change? So, always some exceptions. Can you write me a second rule that flips this around? Jordan, what would you say? Good. When the unit gets smaller, when I go from a large unit to a small unit, when I go from describing a big scale to a small scale, then the number in front of it should increase. It goes from being a small number on a big scale to being a larger number on a small scale. Can we apply this and see how it works? Let's start simple. I found that my weight was 7,200 grams. 7,200 grams. That's a big number and a relatively small unit. Let's make the number smaller. How do I do that? Make the unit bigger. So I want to do some dimensional analysis, and at the end, I want to have units of kilograms. Take 30 seconds to think about where you're going to plug units into this dimensional analysis and what numbers you'll plug into this dimensional analysis. And if you have your calculators, feel free to get them out. We might be doing some more exercises that require you to have some calculations. And I do want to encourage you guys to, maybe I've said this, but I want to say it again. I want to encourage you guys to really get to know the calculator you're bringing with you to the midterm exam. Because you don't want to show up to the midterm and be like, I don't really know how to use scientific notation on this calculator. Okay, tell me, where did you put the unit gram? Why? I don't want grams anymore based on my answer, so it needs to go on the bottom to cancel it. What unit did you put on the top? Kilograms, kg. Now, there are two relationships between grams and kilograms. I'm going to show you both of them, and I want you to decide which one you like better. One of the relationships is that 1 kilogram is 1,000 grams. 1,000 or 1 times 10 to the third. Small number, big unit. Small unit, big number. Meaning that they represent the exact same thing. The other relationship that they have is that 1 gram is 1/1000th of a kilogram. 0.001 kilogram. Does that make sense? That they have two relationships. Berkeley, big unit or small unit? Big number or small number? Compared to this, big. Small unit, big number. Mark, small unit or big unit? Small number or big number? Big unit, small number. Big unit, small number. Relative to the other number in the conversion. Raise of hands. Who of you like this relationship better between kilograms and grams? Who likes this one better? That's okay. It doesn't have feelings. You don't have to like it. But do you see how there are two ways to set it up? You're just changing the scale of the numbers. All right, what's the answer? 72 kilograms. Good. Good job, guys. Who said 72? No, I said it in my head too, because that's what I was going for. Remember, we talked a lot about 72 kilograms in the last class. But you are absolutely right. Sorry, didn't mean to scare you. Is there another way that we could write it? Think about it if we had it this way. We could say it's 7,200 times 10 to the negative third kilograms, which is a bit wrong because it breaks scientific notation rules. You don't have a number between 1 and 10 anymore. You have a number that is much larger than 10. And it's like trying to cancel itself out. 7,200 times 1/1000th.
Where did you get 10 to the negative 3 on the second equation?
Good question. So notice the relationship between base and kilo is a factor of 10 to the 3. So how did I get negative 3? Well, I set grams to be 1. So rather than saying 1 kilogram is 1,000 times 1,000 grams, I said that 1 gram is 1,000 times smaller than a kilogram. I took this number and I divided by 1,000 to make it 1, which means I also have to take this number and divide it by 1,000.
So you just did the inverse?
Kind of,
First one?
yeah. And most people agreed this makes more sense to them. Just have nice numbers. These numbers are challenging.
Which one do you use?
The one on top. But how many times have I seen students use the one on top but flip where the numbers go? All the time. So the way that I try to nail it into you is check. Does your big unit have a small number? And does your small unit have a big number? That's the second tip here. Big unit. Small number. With a small unit having a big number. In this dimensional analysis, this unit conversion, we have used a conversion factor. That's basically what we're looking at here. Conversion factor. For example, 1 kilogram over 1,000 grams, which is equal to 1/1000th of a kilogram over 1 gram. That's a conversion factor, and they are exactly equal to each other. I'm going to actually add another line to this. These are also equal to 1 gram over 1,000th of a kilogram, or 1,000 grams over 1 kilogram. Can someone just point out to me what's different about this form and this form of the conversion factor? Yeah, the ratio has just flipped, right? Exactly. It changes how you use the units, what you cancel, what you get in the end. So, I'm not trying to tell you that every time you use a conversion factor of grams and kilograms, grams has to go on the bottom. Not true. You decided that on your own at the beginning. You decide it based on what you need. All right, I wanted to do one more. The wavelength of light that we were looking at the other day. I want to convert 2.52 times 10 to the negative 9th meters. That is a wavelength of light from crest to crest. I want to get that into a more digestible number. So, work for about 30 seconds to see how to set up a dimensional analysis, what you would want to convert it into. And I think I made a mistake, so I don't want it to be times 10 to the negative 9. I want it to be times 10 to the negative 7. Sorry. Figure out what conversion you want to do, what unit you want to convert it into. There's no wrong answers inherently. Figure out how you want to set it up. Take about 30 seconds to just think about how you want to set it up. Meters, that's the unit. How can you convert this measurement to make it more digestible? If you don't know what to convert it into, what unit do you already know how to put into the dimensional analysis? All right, turn to the people next to you. Talk together. What's stumping you? What step do you know how to make? What step do you not know how to make? Talk with each other for about a minute. Do you have a big number or a small number?
Oh, when I do my
You want to convert to kilometers, right? Is that a bigger unit or a smaller unit?
yeah, sorry.
So what's that going to do to this small number? Is it going to make it bigger or is it going to make it smaller? I don't think kilometers is going to help it make so that the number gets bigger. Good.
So if we divide by a small number,
What do you guys think?
I think it's divide by
Do you have a small number or a big number?
right?
Do you want to make that bigger or smaller? So how should you change the unit? Now the idea is how small. Make it that much. Big number or small number? Which unit?
So yeah, that would give me.
Do you want to make the unit bigger?
I did micro. So this is you have one micro. That. Just a.
Bigger.
I think.
Now the idea is how small. All right, guys. Here's what I was asking a few of you. Do you have a big number or a small number? Small number. To make it more digestible, do you want to make it even smaller or do you want to make it even bigger? Let's make it bigger. So it's on the scale of like 1 to 10 to 100 or something like that. If I want to make this bigger, should my unit get bigger or smaller?
Smaller.
Why?
Because meter is inconvenient, then we have to -7. We want to go in the other direction.
I want to go to a smaller unit so that my number gets larger. Or what you all identified right away, I want to get to a larger number, therefore I need to go to a smaller unit. That's the process. Does that make sense? And I noticed a few of you, your first instinct was actually, I'm going to go to kilometers and see what happens. Well, when I go to a larger unit, my number is going to get smaller. That's not going to help me get it more digestible. You got a question?
Yeah, so when you're putting it in the calculator, do you use E or times 10 to the...
This is a great question. Everybody's calculator is a little bit different. Sometimes it's easier to use that E function to raise something into scientific notation. Sometimes it's easier to do times 10 to the, or your calculator may have a times 10 to the function. However, I don't really trust my calculator that much when I'm using the times 10 to the function. So I put in parentheses anywhere I can. I want my calculator to not be confused about what operation I want done. For instance, I don't want it to think that I'm saying 2.5 times 10 to the negative 7 by having times 10 to the negative 7 times 1,000. You know what negative 7 times 1,000 is? Negative 7,000. And I don't want it to think that is the exponent. So I put parentheses as often as I can. Parentheses, 2.52 times 10 to the negative 7, end parentheses. Then I do multiplied by or divided by my function. So you need to play around with yours to know that you can trust it. And I'm happy to come around and help you look at your calculator to make sure that you can trust it. All right, so I want to get out of meters. This is what I was asking earlier. Whether you want to go bigger or smaller, doesn't really matter. Your first step is to get out of meters. So put it on the bottom. Now we want to go to a smaller unit so that our number gets larger. So let's pick a unit. What intuition do you guys have? Edgar?
Nano.
You want to go to nano. Ryan? Nano.
Micro.
You want to go to micro. We can play around and do both. Why don't we first go to micro since it's closer to our base, and if it's not quite there, then we'll take it a step further and we'll go to nano.
It's not between 1 and 10.
But that's okay. It doesn't need to be if we're getting rid of scientific notation.
Okay.
But that's a. Oh, you're saying nano gets out of between 1 and 10. Yeah.
They both do.
Neither of them are. Yeah. Okay. Well then, why did you want micro?
Because micro is like 0.252, and that makes a lot more sense to my brain rather than like 250,000,000,000,000.
Well, I don't think a factor of 1,000 is going to make all those zeros afterwards.
I think I might have put it in my calculator wrong.
Maybe. Well, then let's go to nano, since I had 2 out of 3 people tell me nano. All right, I'm going to put nanometers on the top. The first step is done. We have put in our units. Notice how you can set up your dimensional analysis without any numbers. That is a big piece of advice. Set up your units first. Forget about the numbers. You can always figure out those numbers later. Units first.
Is that also in like multi-step?
Yep. Whether you're converting 1 unit or 8, set up your units first. All right? Now let's figure out the numbers. Where do you want to put 1? Do you want to put 1 with the larger unit or the smaller unit? You want to put 1 with the smaller unit? Because the small unit has a big number, and if the small unit has 1, that means that 1 is the big number. Does 1 feel like a big number to you? Because here's an example where we did 1 as the big number, small unit, and the small number was in scientific notation, or this decimal. So, one more time. You want to put 1 with the small unit? That would be the big number. Or do you want to put 1 with the big unit? Let's play around and see what we find out. I think the first initial response was, let's put 1 with the small unit. Did I hear that right? Okay. 1 nanometer is how many meters? Nanometer is the small unit, which means that it has the big number. 1 is bigger than what? 1 times 10 to the negative 9th. So with my big unit, I put in 1 times 10 to the negative 9th. Small scale, big number. Big scale, small number. Is that what you wanted? Really? Okay. I like it the other way, and I thought you guys said you liked it the other way too. If we flipped this, 2.52 times 10 to the negative 7th meters times, let's say that I put 1 meter on the bottom, big unit, small number. What is the big number that goes with my small unit? 1 times 10 to the power of 9. Good. Which one is correct? Both are correct. Now, Kristen, I think, is looking at this saying, yeah, but that says negative 9, and that on the bottom doesn't say negative 9. Did you say that in your head?
I thought the base unit always gets the exponent.
Doesn't have to.
Really?
No. Remember, both of these are correct. 1 kilogram over 1,000 grams, and 1 times 10 to the negative 3rd kilograms over 1 gram. They are the exact same relationship, just divided by 1,000. It's your choice. You get to pick whatever you want. They're the same. My plea to you is that you focus on this when filling in your conversion factor. Make sure that you check that your big unit has the smaller number and that your small unit has the bigger number. Small scale, big number, big scale, small number. Feel it out, practice with it, prove that that's right. If you don't like it, find another way to remember it. But that's how I want you guys to try and prove that you're setting up your dimensional analysis right. Both of those setups give the exact same thing. Either I divide by 10 to the negative 9th, or I multiply by 10 to the 9th. Here's a fun thing about exponents. Hopefully you guys remember this from math. When you divide by a negative exponent, it's the same as multiplying by a positive exponent. Just for an analysis, inverse seconds, s to the minus 1, is 1 over s. Multiplying by a negative exponent, the same as dividing by a positive exponent. Dividing by a negative exponent is the same as multiplying by a positive exponent. These are the same thing.
But isn't 10 to the negative 9 nanometers and then 10 to 9
Tera, or meg,
giga?
giga.
Yeah, like,
It depends on how you're setting this up. So this was relative to the base. When the base is 1, no, it's not when the base is 1. This is what's confusing about this scale. And this scale is not the Bible. I want you to remember that as the Bible. The rule of thumb is when you've got your small number with your small unit, then the big unit has to be even smaller. A nanometer is 1 billionth of a meter. That's true. A nanometer is 1 billionth of a meter. A nanometer is 1 billionth of a meter. That means that 1 billion nanometers is 1 meter. A nanometer, I have a billion of them.
oh, okay.
1 nanometer is a billionth of a meter. I have a billion nanometers, that's 1 meter. I know it's trippy. So what do you do to master it?
Repetition.
Edgar?
I just add the zeros instead of dealing with negatives. I just add the zeros, and my scientific calculator can handle it no problem.
I was going to say repetition as well. Practice, 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 but put in your zeros if you need to. All right, 2 different ways to look at this. 2.52 times 10 to the negative 7th divided by 1 times 10 to the negative 9th. That is 2.52 divided by 1, 2.52, and 10 to the negative 7th minus 10 to the negative 9th. So negative 7 minus negative 9, that's negative 7 plus 9. So this gives me 2.52 times 10 to the 2, meters cancels, nanometers. Down here, 2.52 times 10 to the negative 7th times 1 times 10 to the 9th. 2.52 times 1, 2.52. 10 to the negative 7th plus 10 to the 9th. Negative 7 plus 9, same exact answer. Earlier, Lizzie, you said neither of them fall between.
I was just, 'cause I didn't do it in scientific.
We didn't do it in scientific notation.
Yeah, if you don't put it in scientific.
But we can break this out of scientific notation. Some of you might be saying 2.52 times 10 to the second is not easier for me to digest than 2.52 times 10 to the negative 7th. So we can rewrite this as 252 nanometers. And now on the spectrum of light, that falls into the ultraviolet range. That wavelength represents ultraviolet light. Okay? I want you guys to do something a little bit more challenging now. I want you to convert multiple units. So the density of one of my liquids is 0.798 grams per milliliter.
Sorry, I was just gonna ask, how did you get a positive 2 with the negative 7 and the negative 9? Because if you add them, it's negative 16.
But you're not adding. Exponents that are divided by each other, you can actually subtract them. So when I have this 10 to the negative 7th divided by 10 to the negative 9th, I can actually just focus here on the exponent powers, and I can rewrite it as negative 7 minus negative 9. Similarly, when I have 10 to the negative 7 times 10 to the positive 9, I just focus on the exponents, and I can write that as negative 7 plus 9. And these two things are exactly the same. Dividing by a negative is the same as multiplying by a positive. And the nice thing about those exponents is that you can just do addition and subtraction with them, but then you have to preserve the time 10 when you're done. Yeah, so either of these give you 10 to the second. Good. So I have a liquid, 0.798 grams per milliliter. Per how many milliliters? Per 1. It's not explicitly stated, and oftentimes it's written oddly, right? 0.798 grams / ml. But there is a 1 there. If you're driving 60 miles per hour, how many hours to drive 60 miles? 1. That's what we're saying implicitly, not explicitly. So when you hear per something, it's per 1 of that something. That's implied. All right. I want you to give me the density of this liquid in kilograms per liter. You need to not only change grams, you need to also change liters. Change the dimensions of this measurement. I want to give you one piece of advice. You can do this separately, change one unit, then change the next, or you can do it consecutively. Did I say that wrong? You can do it stepwise, change one then the other, or you can do it all at once and just elongate your conversion. Do whichever one makes sense to you right now. Bummer. I guess I erased it, huh? Which one is the bigger unit? So which one has the bigger number? Yeah. So, milli? Good. The reason I don't want to just give it to you is because I know you've got it in your notes. I want you to know how to use your notes. On my end, I actually have it open on a specific date, and it doesn't have that requirement, which means it should have always been accessible. Okay, I wonder if there's a calendar assignment, which is it says take the practice quiz, and you try that, say, there's no one to take the quiz. So I would say go to the module, because the module will have the calendar. Go to the module. That's right. You'll probably get it.
Or just taking it and dividing it by a probability. Is the ratio?
Turn to the people next to you with however far you've gotten. Ask them if they're on the same track. Ask them if they had a different thought process. See how you guys are doing. But you can do either. It just makes more sense to me to have the one in front. One times n. Because no, I don't think so.
Wait, where did you get that?
I think it's about that.
Okay, so.
Yeah. No, you kind of give it away. Oh, you know what I wanted to do? Yeah, I wanted to convert it into cubic meter. I'll do that one now. Well, maybe I won't do that one. I do want to do one with things. But you're right. 1,000 grams per kilogram. 1,000 grams. No, I was thinking about cubic meters. A lot of times, if you Google NCO liquid online, Google will find a source and just push it to you that says like some hundreds or thousands of kilograms per cubic meter. And like I said earlier, there's 1,000 liters in 1 cubic meter. So if I converted that to kilograms per cubic meter, then I multiply it by 1,000. That's what I was going for. You didn't do that. I agree. Yeah. So I did it separately. Sure. Well, you're just for liters. Just for yes. So like, well, actually, no. In this case, liters.
Are you talking about this?
No, you have this already. And you're also.
It's not even on here.
So then, what did you get? All right, guys. 2 ways to do this. Change one unit, get your answer, and then change the other unit and get your answer. Or do it all at once. Since I have 2 units to change, I'm going to add a box to my diagram. And I can change either unit at either time. This is all multiplication, and your math teachers taught you that there is something called the distributive property of multiplication. So it doesn't matter if you multiply 2 times 3 times 4 or 2 times 4 times 3. You get the same final answer. So whichever conversion factor can go in either spot. But I will need a conversion factor from grams to kilograms and from milliliters to liters. Which one do you guys want to do first?
Milliliters to liters.
Milliliters to liters. Where does milliliters need to go in this first box? Top or bottom?
Bottom.
Oh.
I need it to cancel, right? Which means it needs to be opposite of where it is now. And then what goes on bottom? I know I want liters, and notice where liters is in the final answer. It's on the bottom. So I want liters on the bottom. This is a conversion between milliliters and liters. Those are the only relationship that I have. Then I want to get rid of grams. It's on top. Where does it go? What goes on the top? Kilograms. Now, what's the relationship between milliliters and liters? By the way, we've done first step. Units first, then the numbers. What's the smaller unit? Where do you want to put 1,000, Edgar? Their relationship is a factor of 1,000, but
I would say on top.
yeah? So what's the smaller unit? Which one gets the bigger number? The smaller unit or the bigger number? Unit. Right. Smaller unit, bigger number. The relationship is a factor of 1,000. 1,000 milliliters per 1 liter. I have a lot of a small unit or a little of a big unit. What's the relationship between grams and kilograms? 1,000. Which one gets the bigger number? Smaller unit, grams. So there are 1,000 grams in 1 kilogram. What do you notice about my thousands? Do you need your calculator? This gives you 0.978 kilograms per liter. I really tripped up Mark on this one. He's like, I got the same number, nothing changed. Yeah, you've changed your dimensions, and yet the ratio is exactly the same. Now, if we change this into kilograms per cubic meter, I don't need to change kilograms at all. I just need to change liters into cubic meters. Where does liters go? Top or bottom?
Top.
Good, it needs to cancel. Where does cubic meters go? What's the conversion factor? They're not 1-to-1. They are a difference of 1,000. And this one is less intuitive about which is the bigger, which is the smaller. And those conversion factors that are less intuitive, those are often given to you so you don't have to guess. So, earlier when I gave this to you, what was their relationship? Pamela? 1,000 liters per cubic meter. Good. All right. So here I multiply by 1,000. What answer do I get? 798. Good. Kilograms per cubic meter. And Gabriel, if I wanted to write this in scientific notation, what would I get? Laura? If I wanted to write this in scientific notation? No? No. No. Brian?
So wouldn't it just be, because technically you have a decimal to the right of the 8, so you would move it to the left twice. So that'd be 7.98 times 10 to the second power.
Laura, is it true that I want a number between 1 and 10 for scientific notation?
Yeah.
Gabriel is 7 point something, a number between 1 and 10? Good. So I'm going to move it to the left twice, 7.98. And now the question was, or the question is it times 10 to the negative 2, because I moved it 2 spots, or is it times 10 to the second? And I think I gave you guys the wrong idea last class. So let's talk about it again.
It would be positive because you need to move the decimal to the right too, and you're making it a bigger number.
Well, I'm making the number smaller, so the exponent on 10 needs to help it get back to that. Right. So, what's the relationship between 7.98 and 798? A factor of 100. I would need to multiply 7.98 by 100 to get back to this. So I want positive 2 here. When you move the decimal place to the left, your exponent should get more positive. When you move your decimal point to the right, your exponent should get more negative. Kilograms per cubic meter. Good work. Okay. I just realized something. My notes were flipped, so we were doing dimensional analysis after talking about sig figs, which is okay because all of the analyses we did here, they didn't really depend on sig figs. So I want to give you guys a break before I really break your brains with sig figs. And I know you guys have already had them broken, so we're going to try and continue breaking together, all right? Let's take 5 minutes, get up, move around, get your blood flowing, and we'll come back in.
When we think about where we put one and where we put a bigger number, can we just think about that the new unit always gets one in our, chart? Because at least in all of the examples which we did today, new units got always one, and we have we don't need to think about where to put the bigger number or small number, but just automatically put one to a new unit.
That is an interesting observation, Alina. The new unit always got 1. Here it didn't have to. And personally, I like thinking of 1 billion nanometers in 1 meter, but it seemed like the class actually liked saying that 1 nanometer was a billionth of a meter. But so you were right, the new unit gets 1, and the old unit then gets a negative exponent. That's a really good observation. I just don't know if we can say it for certain. So it's a gamble. Plus, think about the relationship between centimeters and inches. If your new unit is inches, then it gets 1. But if your new unit is centimeters, you still have to put 1 with inches. So in the context of the base to prefix, you might be onto something. Don't know. It might be a good way to look at it. Just be cautious leaning into that rule. 'Cause it's not one that I've ever seen somebody notice before. Lean in with caution. Does that make sense? Okay. You're welcome.
I'm wondering, I know I was like an hour late. I'm wondering if I could still do get the attendance.
Yes.
Okay.
I actually haven't done it yet.
Awesome.
And I normally do it during this break period. So
Okay.
as long as you're here. Actually, were you here yesterday? Or last class, Monday?
I was not here on Monday.
Because I guess I could have swore I saw you in the first hour, and then when I went to do attendance, I didn't see you, and I was like, maybe I'm just crazy. But yeah, I've got you down.
Okay, cool. Yeah, I had an appointment at 10, so I kind of have to rush over to get here
Totally.
by 11.
Yeah. Well, I appreciate you making it.
Yeah, hopefully. Luckily, my long appointment isn't until Friday, so I have no classes on Friday.
Isn't that nice?
But what were we talking? So we were talking about the conversion factors.
Pretty much all day. We just talked about the conversion factors.
Awesome.
Yep.
Okay, cool. I'm taking only science, so I've got chemistry and biology and physics all at once. So
Yeah.
we're kind of going over the same thing in every single class, which is good.
Yes.
It's actually really good. I would recommend actually taking all the science.
I did that. I did that one semester, and it kind of broke my brain. When I was in college, I took animal biology, Gen Chem 1, and Calc 1 all the same semester, or maybe there was physics in there too. But I remember I started watching Glee that semester because I was like, I need some drama in my life. I need something that's not just hard science.
Yeah. I don't know. It's kind of, I don't know. I've always really enjoyed science, but it's kind of cool because it's all just different aspects of the same theme.
Mm-hmm.
So, I don't know.
That's a good point.
I would also, I kind of wish I was taking this. I haven't taken trig yet, but for physics, I kind of need trig.
Right.
So, I kind of wish I took trig at the same time. It's kind of going right along with that right now.
Yeah.
So now I kind of have to just guess. But my husband is taking trig, and my physics class, and my biology class with me. He's taking trig on top of it. So I'm like,
So he's just not taking chemistry.
yeah. So he's just not taking chemistry. He's doing 2 other classes instead of chemistry.
Dang.
And so with all my physics homework, I'm like, help me. So it's kind of nice having someone that knows how to do it.
That's good. Yeah.
So it's kind of cool.
Partners in crime and class.
It actually is really cool. I'm going into the clinical side of genetics, and he's going into the laboratory side of genetics.
Nice.
So if we could work at the same place, that would be really cool.
Get into the same.
Interact with the patients and then bring it to the lab. Yeah.
Get into the same programs. That'd be sweet.
Yeah.
Good for you.
It's going to be a lot of fun. After, but, of course, he's getting his PhD, and I'm only getting a master's. So we gotta
Only
get split off after that.
is not the way to look at it. They are different beasts entirely. Yeah.
Yeah. I don't know.
I think I shared on the first day I was in line for a PhD and left it because it wasn't what I wanted.
Yeah.
So don't think that a PhD changes. It's not a different hierarchy. It's a different path.
Yeah, I don't know. I just always thought of it as like a master's and a PhD.
Mine was PhD from a bachelor's,
Oh, really?
no master's. So my friends that stayed in the program and graduated with their PhDs, they don't have master's degrees.
Yeah, he's not planning on getting a master's.
Right,
He's just
right.
gonna go straight to the PhD.
And maybe you'll get through the master's and watch him do his PhD and say, yeah, I can do that.
Yeah, maybe. We'll see. I don't know. It's kind of hard to like work around the kids because I cannot do homework at home. I can't do it.
I hear you. I hear you.
A 1-year-old and a 9-year-old. So it's kind of, I cannot do it at home. It has to be in one class.
Yeah, that makes it a job. All right, guys. What is dimensional analysis? Unit conversion. Taking your measurement in one form and just changing its form. How often does it change the actual value of the number of your measurement? Sometimes, often, but not always. Do you guys have lingering questions about unit analysis, dimensional analysis? Almost.
Ask it, Brian.
Okay. What I would say is make sure that you are practicing with your calculator. Doing things in scientific notation especially. If you're getting numbers that you're not expecting, then it means your calculator is betraying you, and you may need to start using parentheses to trap things in so that it can't do orders of operation weird for you, okay? All right, let's talk about significant figures. I gave a student a ruler and asked them to measure how long this table was. They came back and told me that my table measured 256.7891 centimeters. Do you believe them? Why not? That's kind of rude of you. You don't even know them.
What ruler are they using so they can get that precise?
Oh. You think that's pretty precise?
Also, it could be way more precise.
Well, I think what you're saying is how accurate they were. We don't know how accurate they were. You're right, it could keep going on. Why didn't they get down to the Planck length and tell me the edge of the last electron cloud? Well, let's think about this in terms of, this is centimeters. Let's think about it in terms of millimeters. Can you tell me how this number changes when we look at millimeters? It gets bigger or smaller? The number gets bigger because millimeters is smaller. And between centimeters and millimeters, what's the relationship? Times 10 times 100 times 1,000? Centimeters to millimeters? Times 10. Centimeter is 10 to the negative 2 meters. Millimeter is 10 to the negative 3. If needed, we can take centimeters, convert to meters, and then meters to millimeters. But if I wanted to look at this in millimeters, this is what I have, which means that my student is telling me down to the nanometer. They're telling me that this has 2,567,891 nanometers long. Or, in other words, in scientific notation, 2.56891 times 10 to the 1, 2, 3, 4, 5, 6. Just move my decimal place to the left 6 places. Have you ever seen a ruler that measures to the nanometer? You think I got something wrong there? You know, Ryan's got a good point. That's why I let him talk in class. It's not nanometer, is it? It is micrometer. What's the next smallest unit past milli? Micro. Thank you. Instead of nm, I should have mu m, or a U looking thing. But have you ever seen a ruler that measures to the micrometer? Me either. That is incredibly precise. So how did they get there? Well, maybe it turns out they didn't even measure on the side of the ruler that had centimeters and millimeters. They actually measured on the side with inches, and then they converted it into centimeters, and because of that conversion, it left some weird numbers in there. It gave some trailing. And they just thought, every number my calculator pumps out, I'm going to report that number. So they reported all of it. Now, you guys will never be expected to know the conversion between centimeters and inches because that's kind of an obscure one. So anytime you need to do it on a unit test or an exam, those obscure conversions are given to you when they're needed. Sometimes they're given to you even when they're not needed, which throws you off. But if you don't need something and it's there, ignore it. So let's take a step back. Let's do a dimensional analysis. 256.7891 centimeters. And let's figure out what this student actually measured in inches. Well, the conversion is 1 inch is 2.52 centimeters. Can you plug that into your calculators and see what you have? For what?
For centimeters, 2.57?
2.52.
Okay.
My sevens have a little cross through them. Oof, well, I don't think this example works exactly the way I'm hoping it would, but
102.
yeah. You're making an assumption there. You're not reporting everything that's on there. Yeah, my calculator is saying 101.9000. So I guess maybe let's just go with that. Let's say that this student measured, it was 101.9 inches. Does that seem reasonable? Could a student have measured 101.9 inches. Now, inches don't usually go by the tenths. They go by the 5/8, the 7/16, the 3/4, but it seems much more feasible. So let's say that my student did measure this, and then they converted it into centimeters, and just everything that came with the calculator was what they reported. What should they have actually reported? If this is what they got, what should they have actually reported?
They should have reported to the least number of significant figures doing division or multiplication.
Good. So their number has 4 digits that are all significant. A 1 in the hundreds place, a 0 in the tens place, a 1 in the ones place, and a 9 in the tenths place. Those are all significant to the measurement that they had. Then all of those numbers that were significant to the measurement they had should have fed back into their conversion. These 4 numbers were significant to their report. The rest of them obscured their actual answer, made me think that they worked with a very special ruler, but they didn't. They lied to me. This is a good question. 2.52 in their conversion. I multiplied by that. That has less digits than this. This conversion between centimeters and inches is an exact conversion. You should think of it like counting. 2.52 here actually comes with infinite significant figures. Infinite sig figs. So that number will never limit your significant figures. In the same way, 1,000 to 1, that's counted, that's exact. 1,000 to 1 does not limit you, because otherwise 1 would just limit you to 1 sig fig. Could you imagine if your whole value got limited to 1 sig fig because of your conversion? But 1 to 1,000, that's counting. That is an exact number. This doesn't feel as exact. It feels like somebody must have measured it, but in the scientific community, it's accepted as a ratio. Oh, I wrote it down wrong, though. Oh, isn't that a shame? It's not 2.52. It's 2.54. I'm sorry. You should tell me that. How many times have I made a mistake in the last 2 weeks? Don't answer that. For the sake of this analysis, let's just go with this, okay? I know it's not a great example. I should have prepared better in advance. But let's just go with this. That's not what my calculator pumps out. It pumps out 098, blah, blah, blah. But you guys see the point, right? When you're taking a measurement, you're given some numbers that are significant, some that are not. What part of my student's measurement was uncertain? Was my student uncertain that there were at least 100 inches? Were they uncertain that there was a 0 in the tens place or a 1 in the ones place? What about this 0 in the tenths place? That last digit in your measurement, we talked about this on Monday, that last digit is always uncertain. You're usually using an instrument and you have to guess at that. Or in the case of digital instruments, they're rounding somehow. And so you're always uncertain about that last digit. There might be things after it. So this student is uncertain about this last 0, but it's still significant because it's not 1 and it's not 2 and it's not 3. It is 0. It's just they're not totally certain about it. Okay, that's the idea of significant figures. How do you decide if a number is significant or not? Sig figs, just to round this out. Sig figs include The uncertain digit. All non-zeros. All zeros that are captive zeros are zeros that are between non-zero numbers. Captive makes sense there? Trailing zeros trailing what? Not trailing a decimal inherently.
Trailing the last whole number.
Trailing a non-zero. But they're only significant trailing zeros if there is a non-zero number. This zero is trailing, and the number has a decimal point. So that is a significant zero. Significant figures excludes leading zeros and trailing zeros without a decimal place. It's been cool to look at your guys' Feynman notes. Actually, I don't know if I've read your Feynman notes, but my online students have been reading their Feynman notes for this unit. A lot of them picked significant figures, and they show a lot of examples. So that's what we should try and do, is come up with examples to show these. So let's take this number, 101.0 inches. How many non-zeros? Two. So at least two significant figures. How many captive zeros? One. So at least three significant figures. Is there a decimal place in the number? Good. Are there any trailing zeros after the last non-zero? Yes. Then that trailing zero is also significant. So this has 4 sig figs. Which digit is the uncertain digit? The trailing zero, the 10th place, because that was the last digit in the reported value. All right, how many leading zeros in this number?
None.
I might disagree, to be honest, and say infinite number of leading zeros, but why would you write them out? They are insignificant. They don't mean anything to us. All right, another one. 0.000000252 meters. How many significant figures? Start with the bases. How many non-zeros? Good. How many captive zeros? How many trailing zeros? No trailing zeros. The last non-zero is 252, and there are no zeros after that. So there are no trailing zeros. How many leading zeros? 7 that are shown, and an infinite number beyond that. So how many sig figs total? Just these 3. Which of these significant figures is uncertain? That second 2. It's not the 1st place, because it's like the billionth place. So that last 2 is uncertain, because maybe it's 2.5 or 2.52 sorry, 2521, 2522. Maybe it got rounded down to that number, right? We're a little uncertain about it. So if I don't want to write this with all these trailing zeros, this is really where scientific notation comes in handy. I can ignore all the rest of them and write them as 2.52 times 10 to the negative 7th meters. Or I could write it as 252 nanometers. Both of those are useful because now I'm just showing the significant figures.
And that's an example of trailing
No,
zero or
these are leading zeros.
leading.
Yep.
Thank you.
Captive, trailing with a decimal. Yeah.
Perfect. Thank you. So if it was 1.000, then those would be the captive zeros in all characteristics.
Sorry, if it was one, what?
If it was like 1 point instead of the 0, then wouldn't all those be captive and then they would count as 6?
Yeah, 1.000000252. All of those would be captive because they're held between non-zeros. Okay, let's take this. 38 million grams. How many non-zeros? 2. How many captive zeros? 0. None. How many trailing zeros? And does the measurement have a decimal place? So are those trailing zeros significant? No. If you told me that you made a measurement of 38 million grams, I would say, okay, give or take a million. You're not even sure down to the hundredths place, right? So a better way to report this so that you report just the significant figures, 3.8 times 10 to the 7th grams, or we could say 38 megagrams. Now it looks a lot nicer. I'm ignoring all those trailing zeros, and I ignore the fact that they're not significant. Now there are some instances where you have one trailing zero that is significant. You made a measurement to that effect, but the rest were not. And so you can't have a decimal at the end because not all of the trailing zeros are significant. And this is where scientific notation really comes in comes in handy. So let's look at the number 4.6 times 10, 4.60 times 10 to the third. What haven't I done yet? Liters. Hayden, how many sig figs? 2. How many non-zeros? 2. How many captive zeros? Okay, actually times 10 to the third doesn't count as anything. Yep.
So 1 trailing zero, so 3.
Good. So no captive zeros. Good point. I like that. I've never heard that one before. That times 10 to the negative 3, or times 10 to the 3 doesn't mean anything. No captive zeros. One trailing zero with a decimal point. 4.60. That's a decimal point. So 3 sig figs in this number. Okay, what if I didn't want to write it with scientific notation? What if I wanted to write it just as a normal number? Well, I move my decimal place to the right 3 times. So this goes from being 4.60 times 10 to the third liters, and it becomes 4,600 liters. Do you see the issue with not having scientific notation there? it limited me down to 2 sig figs. Because I have 2 trailing zeros, neither of which have a decimal place after them, so they're not significant. Right? And I can't add a decimal place, otherwise they both become significant. And also, it's a little weird to just add a decimal point with nothing after it. So it would be weird to just add a decimal and make both of them significant in the first place. So this number is not a good way of representing my measurement because it doesn't allow me to really express the number of sig figs. Does that make sense? This is where scientific notation really gives us a hand in precision.
So if you ignored scientific notation and basically did like 10 to the 6 for that, you would have like almost triple the amount of sig figs, and all the ones after the non-zero numbers would still count as sig figs. So you'd have all the ones before. No, because those are really. Don't mind me.
Okay. Good, because I was a little lost, sorry.
I am too, don't worry.
All right. So I want you guys to do some practice just on some sig figs. Oops, I forgot my unit. Rewrite this number with 5 sig figs. Show this number and indicate that it has 5 sig figs. $3,805,000. Lost?
I mean, in my head, I'm thinking it will never have 5 sig figs, right? It would have 4.
Well, look at that number on the right, which we would have said has 2 sig figs, but we wrote it in a way that had 3. What I'm having you do is take this example from the bottom and work it in reverse. Write this number to show that it has 5 sig figs. You're saying, as is, it has 4. And I'm telling you, I made a measurement that had 5 sig figs. Demonstrate it in that way. 3 sig figs, right, Brian? 2 sig figs, right, Brian? Well, I wanted to represent it with 3, so I wrote it in a specific way. 4 sig figs, right? Write it in a specific way to demonstrate that there are 5. Berkeley, do you think you have it? What did you write? Okay, only thing I would change there is where your times 10 to the 6 comes and where your grams comes in. We want to say that this number is times 10 to the 6 with grams. Yeah? Someone raise their hand. Alina?
If we convert grams into kilograms, do we still have 5 sig figs?
Could we convert it into kilograms? So another way to write this. So Berkeley's method was put it in scientific notation with 3 non-zeros, a captive 0, and a trailing 0 with a decimal place, all significant. Alina's method is change the unit. In kilograms, this becomes 3,805.0. Alina, is that what you did? 0.0 kilograms. Great. Would you guys agree? that last zero is still a trailing zero with a decimal point. The only way we did it was by changing the unit. Lizzie?
Do the first one with like 8 sig figs and just keep adding zeros?
So the first one doesn't have 8 sig figs. The first one has 4.
Yeah, and to make it 5, we just add an extra zero.
You mean like a decimal, like point zero?
Yeah.
But then you would
Add
count
a
all those
point
three.
here.
You'd count the other three.
Are you saying add more zeros to it?
Okay, so in scientific notation,
This has 5 sig figs.
and if we wanted 6, could we just do 0.80500?
If we wanted 8,
Yeah,
why do you want 8?
just like why did we want 5?
I told you.
Yeah. So you can just,
Yeah.
okay,
For
there's
sure.
not, okay. So
Although
like-
if you wanted 8, you could just keep this number because this is 7. You could just keep this number and put 0.0. And
So
now
there's
they
not
are
like a-
all trailing zeros with a decimal.
there's not a limitation.
Correct. Edgar first and then Jordan.
In a kilogram, we have 5 sig figs, right? And those are all valid.
Those are all valid. Yep, Alina's method totally worked. And you didn't have to go to kilogram, Alina, correct? You could have gone to megagram. You could have said 3.8050 megagram. Just a different unit, but still the zeros are trailing with a decimal point. Do you see the idea here? When your measurement is going to confuse you on how many sig figs there are, scientific notation or scale, different units, can help you put in a decimal point that you don't have and help you better relate those sig figs. Okay, that's the basis of significant figures. I think it was Brian earlier who mentioned the rules with it. So let's just say these real quick.
Hey John, can I ask a clarifying question?
Yeah.
On the top one, the 8050, is that last zero significant because it comes after a non-zero number?
This one?
Not the very top one.
This one.
Yeah.
It's a trailing zero, just like it is here. But now it's a trailing zero, and there's a decimal point in the number.
Okay, sorry. Thank
Yeah.
you.
And there's one version I feel like maybe I haven't spoken about trailing zeros, which would be if I did take this number and I wrote it as 3,805,000.0. These are trailing, correct? They trail the last non-zero. They are trailing, and there is a decimal point in the number. So they are trailing with a decimal point. They don't have to trail the decimal point. They are trailing with a decimal point in the number. So you would have said by instinct, that's a trailing with a decimal, that's significant. But that can't be significant unless these are as well. Yeah?
So that would be 8.
Correct. This becomes 8 significant figures. All of the zeros are significant because the trailing zeros have a decimal point in the number. And then what about these numbers? What about these zeros?
No.
Yeah, they're leading, right? The reason I didn't show them was because they were insignificant in the first point. Okay, rules with sig figs when it comes to calculations. Yeah, same.
Are we going to be asked in this class to prove examples like this where we have to prove if it has 5 significant figures or like the problem that you have on the right where we go from 2 to 3?
Take a number, and if you're given a number, you do have to say how many sig figs there are. And there may be I don't know actually, if you'd see a question that says, how can this number be written to report how many sig figs there are?
Okay.
I don't I think not.
Okay.
But I think that if you can master that exercise of take a number and report it in a way that shows this many sig figs, then you've probably mastered sig figs.
So like the work that you have on the right of the board, like that's not something we would see in this class. Does that make sense? This is more like conceptual. It's like understanding.
Well, to an extent. So you will have to do calculations and then report the number with the right number of sig figs.
Absolutely.
So if you do a calculation and you get this,
Mm-hmm.
you can't report it as this because that's not the right number of sig figs. So you do need to be able to say, I need to change the unit. Or if my unit is locked, I'm not allowed to change my unit, then I need to write it in scientific notation in such a way that the number I got on my calculator is written with the right number of sig figs. So I don't think you'll be handed a question that says, write this number with this many sig figs. Instead, you have to do that with the calculations you get. Okay. Yeah. So let's talk about that. If you're doing addition or subtraction, you limit your decimal places. And here's an example of that. I weighed a truck, a semi-truck, and I found that its mass was 10 million grams. Well, actually, I had a bit of help. So I knew that it was good to this 100,000th place. So this was 10.0 times 10 to the 5 grams. And then I weighed a small rock, and that rock, so here's the truck's mass. That rock had a mass of 25.6 grams. And I put that into here, 25.6 grams. How much does the truck weigh afterwards? Well, 10 million plus 25.6, correct? But I'm limited in my significant figures by the decimal place. So the answer would have been 10 million, 25.6 grams. But in 10.0 times 10 to the negative 5, this is my least amount of decimal places, the 100,000th place. And if you notice, the mass of the rock doesn't even get that large. So in this number, I'm limited to this significant figure. I'm limited to this decimal place. I know a lot of decimal place examples, they actually take place in the decimal places, but some of the most confusing ones are the ones that take place before the decimal place. So what number do I report as the final mass of the truck and the rock? Basically just the mass of the truck. The mass of the rock was insignificant to the mass of the truck, and that's because I'm limited by the least number of decimal places. Are you guys okay with that?
I think I just got confused.
Most common example is 1.111 plus 1.1. I'm limited to the tenths place. One of them went 3 points past the decimal, one went 1 point past the decimal. I'm limited to 1 point past the decimal. Those are easy. This is more challenging. This number is only significant to the 100,000ths place. This is significant to the tenths place. I'm limited to the least number of decimal places. That's here. So my final answer after doing the sum means that I'm only significant here. That's my uncertain digit. And I'm going to round from the number to the right of it. Well, 0 just rounds 0 to 0.
In other words, the rock becomes insignificant to the weight of the truck.
The rock is insignificant to the mass of the truck. Okay, the example I just said but didn't write down. 1.1 gram plus 1.11 gram gives me 2.22 grams, but I'm limited to just 1 decimal point. So the number I write is just 2.2 grams. That's much more common. Rule number 2 was multiplication and division. You limit the actual number of sig figs. So if you have a number with 2 significant figures, a number with 3, your final answer has 3 significant figures. Let's say that you took this 2.52 times 10 to the negative 9th meters. How many sig figs? 3 sig figs. And let's say that you divided this. Well, I don't actually have a good unit conversion to do here. I want to just do something simple. Let's say you divide this by 2.0. Sorry, no unit. Your number would look like 1.06 times 10 to the negative 9th. 3 sig figs, 2 sig figs. This number is limited to 2 sig figs here. And so I have to round from the number after my last sig fig. So I would report this as 1.1 times 10 to the negative 9.
I thought you said that like ones and ratios technically have.
Well, that's the thing. This is a measurement, not an exact number, but I don't have a good example, so that was a bad example. 2.52 divided by 2.0. 1.26. Yeah, maybe. Is that what you're getting on your calculator? Okay. 1.26. Which would round up to either way.
The only reason, why you are using
Yeah, you're right.
2.0 as the sig fig limiter is because it's not a conversion.
No, we're gonna have to finish this on Monday, and my example was flawed because I'm not doing some sort of like measurement there. I'm not doing some sort of conversion. This isn't 2.0 as an exact number. This is 2.0 as a measured value. So I measured it with 2 sig figs.
And so then that is that's the new sig fig.
Correct.
Rather than just using memory. Because
A number with 3 sig figs, a number with 2 sig figs. I'm limited to 2 sig figs.
Because the previous examples with where you have the conversion of one, the exact numbers,
1 to 1,000
it can't be.
does not limit sig figs. Thank you guys for your time. I'll see you on Monday.